we're moving on from evaluation of basic trigonometric functions, and we're going to start taking a look at what these functions look like. And the ultimate question is, what can we use the sine and cosine functions as well as other trigonometric functions to model? So in this section, we're going to just graph the parent functions of the sine and cosine functions, so we'll get an idea of what they look like. We're going to define and also be able to identify characteristics called amplitude, phase shift, period, vertical shift, and as well as translation, or as well as reflections that we've seen in other videos for just the sine and cosine function. And then finally, we're going to define the domain and range of a sine and cosine function. Before you go through any further in this video, okay, make sure that you have a pretty good grasp from the previous videos how to evaluate something like this. So if I were to ask you to evaluate the sine of something like 11 pi 6, now you might not know off the top of your head that that's something like -1/2, okay? But you should be able to figure that out, okay? So if you can't figure this out yet, okay, what I would urge you to do is go back to section 4.2 with the unit circle, okay? And be able to use the unit circle to evaluate those basic sorts of trigonometric functions, okay? Then come back to this, okay? Now, if you feel good about being able to do that, then we can press on. So first thing we have to do is we have to take a look at what does the parent function of the sine look like, okay? So all I'm going to do is I'm going to plug in 0 for the sine function. So, and what we could do is we could use our unit circle to be able to evaluate this. So the sine of 0, now remember, sine is the y coordinate, okay? So that's going to be the y coordinate, okay? And the sine of 0 is going to be 0. So 1 point on our graph is going to be the origin. Okay, I'm going to blow this up just to make it easier for us to plot. Okay, so this is going to be a point on the sine function. All right, sorry it's so big. All right, then we need the sine of pi fourths. Okay, and again, that's the y coordinate at pi fourths, okay, on our unit circle, and that's going to be the square root of 2/2. Now, in our calculator, we should probably get an idea of what root 2/2 is. So root 2/2 is going to be 0.707. I'll say 0.71 because, again, we're going to be graphing this. So this is going to be approximately 0.71. Okay. We're also going to get these values as well. Okay, so if I go into my calculator, pi over 4, so we would have pi fourths is about 0.79. Okay, if I was to go through and approximate that, so this is 0.79. So the 0.79, 0.71 is going to be on our function. So 0.79, maybe right about here, 0.71. Okay, so maybe this right about here. Okay, again, I know that's not really good, but that's about what I got. Pi halves. So the sine of pi halves, okay, if we were to go into the unit circle, is going to be the y coordinate at pi halves, which is going to be 1. Okay, and so we also should figure out what pi halves is in our calculators. Okay, so I'm just going to change this from pi fourths to pi halves. And that's going to be 1.57. Okay, so if we were to go back into our, this is about 1.57. So we would go to 1.5 about, and then all the way up to 1. So we probably get like this point right about here, okay? And again, I'm just estimating this, okay? I know it's not all that good, but it's okay. And what I'm doing is I'm saying like this is 1.2, 1.4, 1.6, all right? Just going in increments of 0.2 on this graph, okay? So that's how I'm plotting these points. At square root of 3/4, we're going to get root 2/2. At pi, we get 0. Okay, and again, I'm just going in the unit circle. I'm going through and looking at these. This is going to be negative root 2/2. This is going to be -1. And we have negative root 2/2 and then 0. Okay, so now I'm going to go into the calculator. Okay, and this one was 1.57, so I need 3 pi fourths. Okay, so 3 pi over 4, 2.4, okay, 2.57, or 37, excuse me, 2.36, excuse me. So this is about 2.36. All right. And remember, this is about 0.71. Okay. So we go to 2.36, which is right about here, and then root 2 over 2. All right. So maybe like right about here. Okay. All right. Sorry, that last dot is on me. That fine. Again, kind of tough to do on the screen. So just give me a little bit of latitude when I'm doing these. All right. These are approximates. Okay. And then we have pi comma 0. Now remember, pi is about 3.14. Okay, so we know that one. Okay, most of us have heard of pi before plenty. So 3.14 is going to be right about here at 0. Okay, so I'm just kind of dotting this in. Okay, so initially we get this sort of thing going on. Okay, so that, but we still want to keep going through. Okay, so let's just get the rest of these values. So we need 5 pi fourths. So I'm going to get 5 pi fourths. And I'm also going to get 7 pi fourths while I'm at it. All right, just because it has the denominator of 4. So I get 3.93 and 5.5. Okay, so it's going to be about 3.93. Okay, and the other one was 5.5, I think. Okay, so 3.93 and 5.5. It's approximately 5.5. We know 2 pi is just double 3.14, 6.28. Okay, approximately again. And then this 3 pi over 2. All right, let's get that one really quickly. So 3 pi over 2. And again, the whole purpose of this is just to kind of get an idea of what the basic sine function looks like. Okay, so 4.71. Okay, so this is about 4.71. All right, so let's plot the rest of these points. Okay, so negative 3.93 and then down to negative 0.71. So maybe like right about here. Okay, and then we have 4.71. I think that's 4.71. Boy, I can't even read my own writing. That's bad. Let's go back to the scientific calculator. So 4.71. All right, so sorry about that. It's a 7 in English. All right, so 4.71, like maybe right about here, and then down to 1, negative 1, so maybe something like right here. Okay, and then we have negative 5.5. Okay, so right here, and then negative root 2 over 2, which is right about here, and then 6.28 and 0 maybe right about here. All right, so the rest of my function for the sine, as best as I can draw it, probably not as best as you can draw it, looks like this. Okay, so now what we call that is we call that one period. Because, let me try to make that actually look like the word period. Sorry about that. Okay, but we also know that if I wanted to, I could also figure out 9 pi fourths. And 9 pi fourths is actually going to be coterminal to pi fourths. So that would be root 2 over 2. Okay. So I would have another point that's going to be like somewhere up here. Okay. Like at 0.71. And the graph would keep going forever. Okay. And so the sine, and also it would keep going in this direction as well. Okay. So the sine function just keeps going over and over and over again and repeating this periodicity. Okay. So we call that one period. We call the sine function periodic because it just keeps going on and on and on forever. Okay. And if you don't believe me, we'll take a look at the graph of the sine function in a moment. All right. So let's just take a look at some of the things that are basic about the sine function. Okay, so like I said, we could plug in some other values and they're going to be coterminal angles, and we could plug in smaller values. So they would be coterminal, and we could just keep following in this pattern forever. The domain of the sine function is all real numbers. Okay, so I can plug in any number. It might not be a nice number, but I can get an output for it. We notice that the highest point on the period is 1. Okay, and we notice that the lowest point, and I didn't draw this really, really, really well. All right, I drew it okay, but it should go something more like this. Okay, and then go up. All right, so maybe I can erase this other one. It's probably going to mess the whole thing up. All right, but But you guys get the idea that the sine function should go through these points, all right? Remember before we talked about the sine function being odd. That means it's going to be symmetric about the origin, okay? And that makes sense because if there's a point up here, there should be another point down here that's equidistant from the origin, okay? And so if we were to keep extending the sine function, it would look like this. And again, we said it's odd, so it's reflexive about the origin. So we have this point here. We would also have another point down here, okay? So that's reflected in the origin. Or if we have this point, which is 2 pi comma 0, we would have another point all the way over here, negative 2 pi 0, okay, because it's that odd function. The range of the function, negative 1 to 1. This is a period, okay? So from here out to 2 pi is the period, okay? So the period of a sine function is, of just the regular sine function is 2 pi, okay? So basically, it takes 2 pi for it to go up, down, down, and then back up, okay? I know that's horrible, all right? Forgive me, all right? So again, period looks something like this. Okay, so that's going to be the period of our sine function. All right. And again, the highest it goes up to is +1, the lowest it goes to is -1. And that's all right here in each of these. All right. In calculus, you'll be doing a lot of this for those of you that have to take calculus, okay, trying to find out these maximum minimum points. All right. So if I was to graph the sine function just on a regular graphing calculator, okay, so if I had y equals the sine of x, okay, so not sure what happened there, but I have two y's in there. That doesn't make any sense. Okay, given that, that's what our sine function should look like. Okay, if I zoom in, okay, so we have this point right here, pi halves comma 1. That's like a maximum of our function, and then down here, we have 3 pi halves -1. So all those points that we plotted, okay? In fact, we could go through. Remember, we had pi fourths, comma, square root of 2 over 2. Okay, that's a that's a point that falls on our function. Okay, and again, if we were to zoom out, we notice that the sine function keeps following this periodic behavior. Okay, um, things that the sine function can model. Okay, so just in real life. Okay, temperature throughout the day. Okay, usually there's a time of day when it reaches the peak. Okay, probably when the sun is closest to the earth for that day, and then it just goes through and it declines, okay? Then it goes back up again the next day, okay? So usually temperature is periodic. Things that are also periodic are going to be sound waves. Okay? So those are periodic, okay? So for those of you that are studying engineering or physics or something like that, you'll see a lot with sound waves, okay? Sound itself is periodic. There's a lot of things that can be modeled by periodicity, okay? If you have like a system that has like a weight on the end of a spring, okay, so just ignore me. I know this is bad, but you know that the spring goes up and down, okay? It has that periodic behavior, okay? So its position after so many seconds is periodic, okay? Because it goes down, and then it goes up, and it goes down, and up, etc. Okay? So those are just some ideas as to why we're finding the graphs of these things, okay? Because we can model things like the temperature versus time, or maybe like the length or the bandwidth of some sort of sound wave at a specific time, or we can model the displacement of a system at a specific time. All right, so the question is, what if we don't have a basic function? Okay, so for instance, and we're going to look at this in the next video, what happens if we have 3 sine of 2x? How does that change the period, and how does that change some of the other things? Okay, so in our next video, we're going to start taking a look at how we can go from this basic function and start taking a look at the other sort of modified versions of the sine function.